What is thermodynamics? Thermodynamics is based on 4 laws. These laws are the 0th law, the 1st law, the 2nd law, and the 3rd law. These laws act as the rules that all thermodynamic interactions abide by. The 0th law states that if two objects are at thermodynamic equilibrium with a third object, these two objects are also in equilibrium with each other. This law is why thermometers work and can show temperature. The 1st law states that energy can not be created or destroyed, only transferred. For example, turning electrical energy into heat or mechanical work. The 2nd law of thermodynamics states that energy naturally flows from a higher state to a lower state. The law is talking about entropy, which is the measure of disorder in a system. This means that the universe's entropy is increasing. This is why when you put a hot cup of coffee in a room, it will over time cool down to the temperature of the room. The 3rd law of thermodynamics states that as you approach 0, the entropy of the system will approach 0. 0 entropy means that there is complete order in the system. So how do we study thermodynamic interactions? We can study the systems that the interactions are happening in. A system is an entity of interests with a well-defined boundary. For example, if we have a glass of water, for this glass of water, we can define an internal boundary. For this case, the internal boundary would be the water inside of the glass, denoted by the area inside the dashed lines. We could also define an external boundary. In this case, of the glass of the water, this would be the area including the glass and the air above the water. There are 3 main types of interactions that can happen across boundaries. You can transfer mass into a system. In the example, the mass transferred would be through an inlet into the system. You can also have heat transfer into a system. This would be through a flame heating the system or other methods, but in this case, through a heating coil. Lastly, you can have work transfer into a system. In this example, in the form of mechanical work being transferred into the system through a fan. The interactions have the following variables: m dot for mass transfer, q dot for heat transfer, and w dot for work transfer. Systems can be defined by certain terminology that quickly describes what is being transferred into the system. The 2 main types are closed systems, which have no mass transfer into the system, and open systems, which have mass can transfer into the system. You can also have unsteady systems as well. An unsteady system is in which states within the system are changing over time. These states are parameters such as pressure, temperature, velocity, or mass. Inversely, steady-state systems are systems in which these parameters do not change over time. There are thermodynamic properties of systems that we can define. There are 3 properties: extrinsic, intrinsic, and extensive properties. Extrinsic properties are properties in which observations depend on the viewer's reference. A common example of extrinsic properties is weight, which can vary from the same object depending on the gravity in which it sits. On the other hand, intrinsic properties do not depend on the viewer's reference. Properties such as pressure and temperature would be intrinsic properties because the viewer's frame of reference or the amount of matter does not matter. Extensive properties are properties that do change depending on the amount of matter that objects possesses. For example, mass and volume would both be extensive properties. We can also study the way the systems change and define the processes that this relates to. There are 4 main types of processes: isothermal, adiabatic, isobaric, and isochoric. An isothermic process is a process that occurs at constant temperature. An adiabatic process occurs without heat exchange to the surrounding, meaning that the system is insulated. Isobaric processes occur at constant pressure. The last process is isochoric, which occurs when there is no change of volume in the system. We can simulate what would happen in the real world when studying a system by models. There are 2 main thermodynamic models: the solid-liquid model and the phase change model. The solid-liquid model simulates transitions of a substance such as water from a solid to liquid. You could use this to simulate the melting point of ice at different conditions. The phase change model simulates transition from one phase to another. For instance, you could simulate water vapor condensing into liquid water. When modeling gases, there are 2 different models that are used in different conditions. The perfect gas model is a way to simulate gas behavior at high pressure. At lower pressures, it's better to use the other model, the ideal gas model. So what can we apply all of these ways to study thermodynamic interactions to? Well, everything, but to some systems that we study involve flow. To simulate these, we categorize them. Pipes, ducts, and tubes are common systems to study. These are long areas of flow that have the same inlet and exit area. Nozzles and diffusers, on the other hand, are like pipes, but instead of having constant inlet and exit velocity, they have two different inlet and exit areas. Compressors and fans and pumps are also systems in which it is put into or taken out of the system involving flow. For example, a turbocharger from a combustion engine would be a compressor. Lastly, we have throttling valves, considered one of the most important inventions in history. A throttling valve is a system in which the flow can be changed. This system is the reason that we have the modern-day refrigerator. So why does it matter? Well, everything in life has some aspect of thermodynamics that interacts within the world. Just to name a few interactions that are heavily affected with thermodynamics are the heat engine and modern-day refrigerators.